My name is Jeremy Kuzub. I'm presenting initial results of the AurorEye project, a highly portable RGB all-sky imager station. It is designed to travel with citizen scientist aurora chasers, complementing their own aurora photography with calibrated, all-sky images suitable for research purposes. Let's look at the motivation for developing the AurorEye system. Citizen scientists have proven to be valuable contributors to aurora science, through observation reports like those logged on aurorasaurus.org website, to imagery of new phenomena that can be analyzed in time and space to better understand auroral phenomena. These aurora chasers are citizen scientists because they work with researchers to analyze and understand what they are seeing. Citizen scientists have also designed software and data visualization products that make existing research imagery more accessible, searchable, and engaging. The aurora chaser community and the research community both collect aurora imaging data. These aurora chasers may use high-performance consumer cameras that feature high-resolution, high-sensitivity, low-noise RGB sensors. They travel to avoid cloud cover and light pollution and study the best locations to capture aurora images and video. Research imaging systems, such as those in the Themis network, are static emplacements designed to work continuously with highly specialized calibrated cameras and co-located instruments like magnetometers and spectrometers. These images from these camera networks can be stitched together over time and space to get a big picture view of aurora activity and combined with data from other ground and space-based instruments, since the imagery is calibrated in location, time, and perspective. The AurorEye project aims to leverage the enthusiasm, know-how, and geographic distribution of citizen scientist aurora chasers by providing a subset of them with a highly portable, self-contained, high-resolution, all-sky aurora imager. This compact system can tag along with the aurora chasers when they go out for a night of photography, requiring a minimum of setup time and no supervision, while acquiring time-lapse all-sky camera imagery at high resolution, calibrated in time, space, and orientation. These units are also designed to be low cost so that the network of them can be distributed geographically to aurora chasers and the data synthesized across a broad geographic area. Let's take a look at the hardware component of AurorEye. The system is built around a consumer APS-C digital camera with a high-sensitivity 24-megapixel CMOS RGB Bayer sensor. The camera internal buffer and SD card storage system allow continuous image capture with exposure times varying from sub-second to 30 seconds. The all-sky image is captured by a consumer 180-degree fisheye lens with an approximately equidistant projection mapping onto the image sensor. The aperture is comparatively large at f2.0 to maximize light capture and minimize required exposure time. AurorEye must function for as long as an aurora chaser is out capturing imagery. A 20 to 30,000 milliamp-hour consumer lithium polymer battery pack can provide the camera and support systems for 8 to 12 hours. In order for AurorEye to be autonomous, an onboard Raspberry Pi single-board computer manages the camera and other sensor systems. This runs Raspbian OS, and the AurorEye software is primarily written in Python. This computer also acts as a small heater for the AurorEye unit, with a power dissipation in the 5-watt range. This computer can connect to local networks via Wi-Fi when AurorEye is in a back-home mode with the Aurora Chaser, in order to offload data. It also acts as a Wi-Fi hotspot in the field, allowing anyone within range to monitor the captured images via smartphone. Additional sensors are used to provide contextual data for the captured image sequences. The primary sensor is a GPS to add accurate time and location data to each image sequence. A 3-axis accelerometer assists with AurorEye setup, providing a bubble level function so the unit can be aligned so that the zenith is in the center of the image frame. Temperature, humidity sensors are included to monitor environment during image capture, which can also be used to understand system performance in the typically cold weather where AurorEye will be deployed. Magnetic compass and magnetometer instruments can also be interfaced as a future enhancement. This hardware is mounted inside a consumer, rugged hard case about the size of a school lunchbox. The camera is mounted on an aluminum rail system with the lens protruding from the top of the case. The bottom of the case is fitted with a standard photographic tripod mount. On the side, a simple interface with glove-friendly controls allows easy setup and stop of the AurorEye time-lapse capture. In a future enhancement, a 3100 series magnetometer will be tested for co-located 10 nanotesla resolution data gathering. Changes in local magnetic field strength are associated with auroral substorms and increased auroral activity. Let's take a look at the software now. The software is written in Python and leverages several existing community software libraries for camera control and image processing. There exists a large ecosystem of Python-compatible sensor libraries allowing upgrade with new capabilities. The software is designed around an abstraction that all sensors are represented by a common sensor object, which has startup, polling, and readout interfaces. Camera commands, status, and imagery are read via USB with the gphoto2 library. The software operates the camera in burst mode, effectively holding down the shutter during an image sequence and taking advantage of the internal high-bandwidth camera bus to write large image files to the SD card. When the user starts AurorEye time-lapse capture, camera images are sent directly to the camera. This allows the Python software on the Raspberry Pi to do near real-time image analysis. And this allows the AurorEye to act on what it is seeing in the image analysis scripts. For example, a script could allow the Raspberry Pi to change the time-lapse rate, i.e. the exposure time, based on analysis of green channel data in the sampled images, so that both quiet and high activity periods of auroral activity can be exposed properly, and faster changes in morphology captured with less smearing over time. Sample images are also used to update Wi-Fi hotspot web server so that anyone near AurorEye with a smartphone can monitor captured images and other near real-time data. Finally, data gathered by the polling sensors such as GPS time and location are logged in a dedicated metadata file associated with the time-lapse image capture sequence. When the Aurora Chaser photographer returns from a night's photography and plugs the AurorEye unit into charge, the system enters a mode where the image data is offloaded from the SD card into a local USB drive. Preliminary image data is made available automatically without user intervention. The image sequence is converted internally to a high-definition 8-bit per channel RGB time-lapse movie which is compact enough to be uploaded to a remote server via the AurorEye Wi-Fi connection. If more analysis is warranted, the 100 to 200 gigabytes of captured data for a single night can be analyzed by requesting upload of individual frames, or even physically mailing the very small SD card via letter mail. Let's look at results and testing. To demonstrate that the GPS time and location tagging of image sequences worked as intended, AurorEye was set up to capture an overhead pass of the International Space Station. The timestamps and location and image data align with expected overhead pass times. This also demonstrates the potential for AurorEye imagery to be used with conjunctions of data monitoring satellites typically used for magnetosphere and ionosphere research. A close-up of the ISS track shows the time gap between two exposures is minimal, demonstrating a high duty cycle for the image capture, meaning there is very little missed time between shutter closed and shutter open for the next image, a valuable characteristic when aurora are changing rapidly. An AurorEye prototype was tested in Canada's Yukon Territory in September 2021 to demonstrate the image capture workflow. An Aurora Chaser carried it as part of carry-on aircraft luggage and operated it in conjunction with their standard photography workflow. Setting up the AurorEye on a standard ball-head tripod was assisted by an artificial horizon interface on AurorEye, ensuring the center of the image was at the zenith. The simple interface already includes default exposure settings, so the next and only task was to press start. AurorEye operated for the remainder of the night with only one intervention to switch from high to low frame rate due to changes in pre- and post-midnight auroral activity. Light pollution from headlamps, headlights, and other sources was minimized by extending the tripod height to 2 meters. Over 900 images were captured at 2 exposure settings. The images were later downloaded via Wi-Fi. And let's take a look at a substorm and recovery sequence captured with 2-second exposures. The resolution of the time-lapse movie was 6,000 by 4,000 pixels with 8-bit depth per channel, RGB. After midnight, aurora activity tended towards pulsating forms, so AurorEye was restarted with new image sequence at 30-second exposures. Another sequence, 400 kilometers further south near Whitehorse. This demonstrates what AurorEye might capture in near auroral zones where there is larger population. Red aurora and clouds with reflected city light are visible. Towards morning, patchy aurora forms are seen moving westward. AurorEye also captures raw images, along with JPEGs. These have a higher dynamic range, as demonstrated in this post-processed frame from the previous time-lapse. This is a single frame from the Aurora time-lapse overhead during the substorm expansion phase. This frame shows the lower altitude magenta emissions from molecular nitrogen directly overhead. Using raw images' high dynamic range, both bright and dim auroral features can be brought within the 8-bit depth of computer displays for sharing and analysis. Let's look at discussion and results. Building and testing the first AurorEye prototypes has resulted in a better understanding of what works and what the next step should be. The first optimization was reducing the size of AurorEye dimensionally to be half the size of the first prototype. This allows it to travel inside carry-on luggage rather than being a piece of luggage. A smaller volume is also easier to temperature control. AurorEye was built without the use of a machine shop. All tools were hand tools. Wiring required only basic soldering, and terminal blocks were used throughout to minimize the manufacture of custom cables. Using an off-the-shelf hard case as the protective shell of AurorEye saves manufacture time and overhead. Along with the use of common off-the-shelf components, this points to AurorEye units being manufacturable by student groups. The units cost approximately USD $800 each, most of which is the camera and lens. The main goal of AurorEye is to have calibrated image sequences of all-sky aurora activity. This was demonstrated with the synchronization of GPS time and location, temperature sensors, and points to extension with other sensors such as high-sensitivity, off-the-shelf magnetometers, such as those being used in other citizen science projects. The high image resolution, sensitivity, and low noise of the consumer image sensors has created a renaissance in creative aurora photography. AurorEye demonstrates that these sensors and the high bandwidth data storage systems in the associated consumer cameras can be leveraged to capture flexible, high-quality data. As demonstrated with the Aurora Dome project, these all-sky sequences can be reprojected into a virtual reality environment, converted to aligned keyogram stacks, and other visualizations. The high bit depth of raw images files also allows greater flexibility in recovering high and low brightness features. Rapid setup was found to be very valuable. The Aurora chasers want to tend to their own camera equipment and photography without having to monitor and deploy a scientific instrument. The 2 to 3 minute time to deploy AurorEye made it an unobtrusive partner, meaning more photographers may be willing to take the instrument to the field and use it. An Aurora chaser with a single camera can effectively double the number of images captured each night, and all-sky lenses can complement their selection of rectilinear lenses, which capture only a select portion of the sky. AurorEye is designed to be autonomous. However, it also acts as an in-place observatory via its Wi-Fi hotspot. Just like a cafe or airport, anyone with a smartphone near AurorEye can see the images it is capturing, which often have more detail than what the human eye sees. This functionality also allows Aurora chasers to check on the AurorEye from a few tens of meters away so they don't feel tethered to the instrument. Next steps in conclusion. Components for 4 units have been acquired for construction, and a campaign of beta testing and feedback will follow. A centralized website of time-lapses needs to be deployed so that a community of AurorEye operators can see how their contributions work together. The data can also be shared to existing citizen science projects such as aurorasaurus.org. A plus or minus 10 nanotesla sensitivity magnetometer is under test and can be integrated into the modular sensor architecture of AurorEye, providing co-located magnetic variation data in 3 axes. Because AurorEye has an architecture that allows the control computer to monitor the images being captured, and because auroral activity varies in brightness and motion rate, a key next step is to automate exposure time adjustment based on green channel delta in brightness and structure. An ongoing challenge with time-lapse imagery is data volume. We cannot expect Aurora chasers to tolerate AurorEye uploading 100 or more gigabytes of data each time they use it. However, the H.264 codec movies have a limited dynamic range of 8 bits per channel. Exploring options such as 10-bit H.264 encoding, developing raw images internally, or using newer compression algorithms such as H.265 may require a more powerful internal computer. Thank you for your time and interest. You can reach out to the author at this email address and follow AurorEye progress on Twitter @CaptureNorth.